Hello, my name is Juan Cabrera-Garcia, and I'm a state extension specialist in horticulture and research assistant professor for University of Missouri. Today, we're going to talk about understanding grow lights, and the reason why we're doing this is because if you shopped around for grow lights, you may have seen that there's many things out there, many definitions, and sometimes it tends to be very confusing. And the purpose of this video is to explain to you the definitions and give you the information so that it is easier for you to navigate all that grow light information out there. First, there are some things you need to consider before purchasing lights. If you're in the planning phase of your production unit, you might be thinking about a full indoor production system or a greenhouse. Just think about sunlight is free, and just by having a greenhouse, you may have significant energy savings in terms of being able to utilize existing sunlight as opposed to full indoor growth production. But regardless of the case, you have to also consider how much it's going to cost you, the initial investment to purchase and set up the lights, and also in the long term, how much it's going to cost. And you can do some long-term projections by making some assumptions based on manufacturer information. Let's say, for example, you're going to run it for 5 years, and let's say you're going to do 8 hours a day, and the manufacturer will tell you how many watts the lights consume per hour, right? So then you can calculate how much it's going to cost you based on your electricity rate per kilowatt hour. Also, you can look at how many times you need to replace the bulbs, right? So that goes into a 5-year projections, and after 5 years, how much it's going to cost. The other thing is if you're growing, and this is mostly true for people that are growing indoors, full indoors. And if you want to grow vertically, you want to stack the production units. You have to think about light sources that can be close to the plants without burning them. In this case, your options are limited to LED lights and fluorescent lamps. High pressure sodium lamps, they tend to generate a lot of heat and they can burn the plant. Also the light coverage, and then the light quantity and quality. And this is what we're going to be talking about moving forward. All right, so let's compare. Obviously, we know that sunlight is free. And then in terms of initial capital investment, high pressure sodium lights are going to be cheaper to acquire, and they're going to have wider coverage areas. So you're going to end up needing less light fixtures as opposed to fluorescent lamp and LED lamps, which you need to put closer to the plants. They're going to be more expensive because the technology itself is more expensive, but also you're going to need more fixtures. LED lights are the most efficient light, hands down. There's no question about it. And fluorescent lights are not as efficient as LEDs, but they're more efficient than high pressure sodium lights. Now, with LEDs, you can control the specific light color. And we're going to talk about that in more detail further on, as opposed to fluorescent lamp and high pressure sodium lamps. Because they're more energy efficient, the LED lamps, they have lower operation costs as opposed to the other two types of lamps. Obviously, sunlight is free, right? Just keep that in mind. And then longevity, LED lamps tend to last longer than both fluorescent and HPS, but fluorescent lasts longer than HPS. HPS is the one that lasts the least of those three types of lights. All right, before talking about light quality, I want you to look at this. You may have seen this in a famous album cover, right? But what I want you to understand is that light is composed of multiple colors, right? If you were able to break down light into its components, you're going to notice that it is a wide ray of sunlight. It's composed of red, yellows, greens, and blue lights, right? And the reason why I'm showing you this is because plants evolved to use some of these colors, not all of them. So that's when we talk about light quality. Is the light in the right color or wavelength for the plants to be able to use it? So the plants used by plants range from 400 to 700 nanometers. And that's what we have here in this graph. On the horizontal axis, we have the wavelength, which also correspond to the colors. And on the vertical axis, this is the relative yield for photosynthesis for a plant. And for those of you who do not know about photosynthesis, that's the process that the plants use to gather light and convert and create sugars for their to feed themselves, right? And we see that there's a peak in terms of the ability of plants to yield sugars using photosynthesis. There's a peak in the blue color, and in the red color. So that's why photosynthesis peaks in blue and reds. Now, let's say you're gonna go to the hardware shop and you're gonna buy lights from Menards or from Home Depot, right? Now, keep in mind that human eye sensitivity is mostly towards the center of these graph. We're more sensitive to green colors and yellow colors, our vision. So if you go by, and that's what we have here in this graph, if you go to a shop and buy, let's say, a bulb, a halogen bulb from the shelf, chances are that bulb is going to have most of the light in the greens and yellows, right? Will you use this bulb to grow plants? Notice how much is in the blue light. And yeah, there's still some red light, right? But you do not have the peaks for blue and red that the plants need for photosynthesis. So this light might not be the best option to grow plants. This is an example of light spectrum from a grow light that's used to grow plants. And notice that this lamp outputs in the blues and it also outputs in the reds, right? So this is a good light for growing plants, not the one down here. So with that said, if you go to the shop, you're gonna notice that the lights that they sell you is gonna say this light has 300 candelas, or let's say, for example, 700 lumens or something like that. Now, these are units that are designed for human eye sensitivity. They do not mean anything for plant growth, right? What we use for plant growth is, and I'm sorry for this, but we scientists like to use acronyms to shorten up terms. We like to name things. The radiation that's active for photosynthesis is called photosynthetically active radiation, and the acronym for this is PAR, right? And it refers to the color of the of light that is usable for plant growth, right? Which is between 400 and 700 nanometers. And in this case, we have lumens here. And notice that if you buy a lamp for lumens, this is what they're trying to reach, right? This is the wavelengths that they try to, that lamp is going to try to output. But if a light is developed for plant growth, it's going to give you the PAR. So it should give you, the lamp should output colors that are usable for plants in this range, 400 to 700. So that's just the color, right? Is the light giving you the right colors for plant growth, right? That's the first thing. Now, how strong is that light? And this is the second acronym, so PPF. Sorry, I have an extra P there, but it's photosynthetic photon flux. I'm sorry for this again, but this just means at the source, how strong is the light? How much light units are coming out of that lamp? That's within the PAR color range, the colors that are useful for plants. So amounts, we use this unit, micromoles, and you're gonna see every second how much light inside the PAR color range this light is putting. That's what PPF means, right at the light source. Now, obviously, you're not gonna put the plants immediately close to the light source, right? You're going to put them at a distance from the light source. So in any given area at a set distance, right, how much light is reaching the plants every second. So this is just reaching a set area at a certain distance, right? What I want you to understand is DLI. DLI refers to the cumulative light that the plant or that area received in one day. How much light. And why this is important? Because there are some recommendations for crops in terms of PPFD and DLI. Now, notice that, let's say, for example, let's go for lettuce. There's a PPFD between 250 and 350. If you go over this number, two things can happen, right? First, over 350, you're not going to see any more plant growth. So the plants may look, let's say you're doing 400 ppfd. That means that the plants are still growing normally, but you're not going to see an increase in yield. So in that case, you're wasting electricity in a response that's not there, right? Second, if you go way over this value, you can damage the plants. And sometimes you're going to see that the plant growth is going to decline if you go over that. So just the intensity at a certain distance, you want to keep an eye on that. And second, what's the maximum amount of light that a plant needs to perform or to grow per day? So that's the DLI, that's the far right column here. Those are recommendations. So let's say, for example, lettuce here, you want to be between 14 and 16 moles per square meter per day. We have PPFD, we have DLI. Let's say we already have the DLI recommendations for plants. How do you know how long to keep the lights on to reach this DLI? Well, if you're doing a greenhouse with sensors and some automated control, in a greenhouse, for example, the sensors will measure the light provided by the sun at sunset, right? So it's, let's say, 5 p.m. And this is how much light the plants got, right? And then you have the set point. You tell the computer that you want to have a DLI of 16. So what the control unit is going to do is that it's just going to turn on the lights till you reach the desired DLI. Now, in indoor production, it's a little bit different because you do not have the external input from the sunlight. So you have to provide the whole amount of light. And that's what we're going to talk about next. Let's say, for example, you're going to purchase this light that you saw online or in a shop. First thing you have to see, what is this light outputting lights in the color wavelengths that you want your plants, in the color wavelengths that the plants are going to be able to use. So notice that we have blues, we have reds, but we also have some ultraviolet, and we also have some far red. And I'm going to explain later the reasons why you want those in some scenarios, right? This light manufacturer is also providing the PPFD map, right? So at, let's say, for example, so if you notice, when you get closer to the plant at a 12 inches distance from the plant, notice that the PPFD numbers tend to be higher, right? Because they're closer to the light source. As you go farther away from the light, 14 inches, the PPFD number gets lower. So let's assume we're gonna set this light at 18 inches from the plant. And we have this PPFD map. So it's telling you how much light is reaching that area at that height. So you need to know how long you're gonna run the lights. Right now we have the PPFD, and let's say, for example, with lettuce, let's go back. With lettuce, let's say we're gonna be growing lettuce, we need a DLI of 16. We have the PPFD map. We know how much light reaches this area at this distance. The question is, how long should I keep the lights on to reach the desired light amount? So the first part is just make an average of by adding the four corners of the PPFD map and the center, and then divide that by 5. And that's what we have here. We have an average of 517.6 PPFD. Then you're just going to multiply that value, that average, by 3,600, and then divide that by 1 million, and you're going to get the total light that reaches this area in 1 hour. So this is the value 1.86, and we divide by 1 million is because this is in micromoles, and we want to get moles, and that's the DLI units from the previous slides. Then last, we just divide the crop requirement. In this case, for example, we said we're going to be growing lettuce. The DLI requirement for lettuce is 16, and we're just going to divide that by that total amount of light that reaches this area in 1 hour. So we need to run this light for 8.6 hours to get the desired DLI. So we talked about previously the different colors, red and blues. Obviously, red colors and blue colors are the ones that you need for photosynthesis. And this is just an explanation on what we know, what those colors do. So red lights promotes growth, tissue expansion, and in tomatoes, far red light triggers flowering. Now, blue light promotes accumulation of phytonutrients and ultraviolet light. And phytonutrients, for those of you who haven't seen this one before, it refers to those compounds that we know that are beneficial to human health. We have made that link between human health and those compounds. Now, the problem is, if you use only blue lights to grow the plants are going to grow shorter. It's not going to expand. It's going to be a stubby little plant, but it's going to be packed with nutrients. So what growers do is that sometimes they will put ultraviolet light lamps mixed in with the regular lights, or they will have a room full with ultraviolet lamps where let's say, for example, you're growing microgreens, and the crop cycle for microgreens, let's say, is 18 days. So you're gonna grow your microgreens under your regular lights for 16 days, but then the last 2 days, you're gonna move those microgreens to that room that only has ultraviolet and blue light to promote the accumulation of those beneficial compounds. And this is just from one manufacturer. That summarizes what I just said about the red, blue, ultraviolet, and far red light. And I hope this information was useful and that you're going to be able to navigate that mix of information out there when purchasing grow lights. But if you still need assistance, just keep in mind that you have a whole team of horticulture experts and myself willing to help you, and you can reach out to us. Thanks.